Hi everyone, my name is Daria, and welcome back to MoE 101 series. Today, we are switching our focus from training to inference. You remember that in part 3, we trained our own MoE model. In part 4, we were able to scale it together to production level size. Now what? We are going to use it. It's either you have a particular application where you want to use that model, or you have a group of users you want to serve, or you just simply want to know more about how to run this inference job efficiently. It's a very different task if you compare inference to training. I can't say it's simpler. It might sound simpler because you don't need gradients, you don't need optimizer states, so less work. However, it has its unique challenges that we are going to discuss and address some of them. It's actually a fun fact that people who train these models sometimes never speak to people who actually use these models. And because of that, some of the design choices we've made during the training stage might not be optimal for the inference. So we are trying to be better as ML researchers, and this is why we do cover inference in MoE 101 series. By the end of this guide, you will learn how to model MoE inference arithmetics, what are the issues you might hit, and how to fix them. Before you kick off your first inference job, let's calculate how much storage it requires to store the model weights, so that we don't have to hit the out-of-memory issues later. I'm going to assume that we are using modern version of the MoE model. So thus, let's assume that we have rotary positional embeddings, untied embeddings, Swee-Glue nonlinearity, layer norms, multi-head attention, and industry standard learned routing. For all the parameters we calculate, we are going to multiply them by k, where k is number of bytes that we need to store per parameter. Thus, you can actually configure that k depending on your setup. For example, for full precision, use k equal to 4. For half precision, you can use k equal to 2. Now, let's calculate amount of storage we require for the full MoE model layer by layer. First goes the embedding layer. There, we need to transform a token ID into its input representation of size h. Let's assume that our vocabulary is of size v. Thus, we need to store weights for our embedding metrics. So you need k multiplied by v multiplied by h bytes. Next goes the layer norm. That one is really tiny. We only need to account for gains and biases, and thus you only need 2 multiplied by k multiplied by h bytes. After that, we have a multi-head attention. There, we need to store k, q, v, and output matrices, each of the size h multiplied by h. And thus, you need 4 kh squared bytes. After that goes the layer norm. We already know how much storage it requires, so we can just double it in our calculations. Afterwards goes the router. A router network transforms your input representation of the token into the expert class label. For that, let's assume that n is number of experts. You require k multiplied by n multiplied by h bytes. Next goes the expert networks themselves. There, we need to account for 3 different projections that each expert performs. One is called up projection. Then goes the gated linear unit that comes from Swee-Glue. And then we have down projection, each of the size h by f multiplier by h. Thus, you require 3k n f multiplier and h squared bytes. We finish off with an output embedding matrix, and it requires the same number of bytes as an input one. Now you can sum up your bytes for a decoder block. That one doesn't include input and output embedding. You multiply that by number of layers, then add your input and output embedding storage requirements. Overall, this is how much storage you require to store model weights. Next thing we will do, we will answer the question how fast this model is expected to run. So then when you actually run it, there are no surprises. For that, we will focus on two different stages that inference has. The first one is called prefill. This is the stage where we process the user input query. The second stage is called decode. This is the stage when the model generates its output. The first stage operates on a sequence level, and the second stage operates on a token level. Because we have autoregressive inference that generates only one token at a time. Similarly to the model storage parameters, we are going through block by block and estimate how much flops it requires to run a particular block. Now, one little prerequisite, check out the block for how much flops it requires to multiply two matrices together. All of the operations we talk about will be based on that. So let's start with an embedding. Embedding needs to multiply a matrix of size S by H by the embedding matrix of size V by H. So thus we need 2 multiplied by S multiplied by V multiplied by H flops. After that goes the layer norm. And layer norm is really tiny. Check out the details in the block why it is 7 by S by H flops. Next goes the attention. In attention, we need to perform first projections. We need to project our token hidden representation into the query, key, and value spaces. So that's the first part of the equation. The second part accounts for the dot products that we perform in the attention compute itself. And the third one accounts for the softmax nonlinearity. Check out the block for details for why it is exactly 3 multiplied by S multiplied by A actually there's S squared, 3S squared A, number of flops. After that, we have layer norm. We already know how to calculate flops for it. After that, we have the router. In the router, there is another matrix to matrix multiplication. You have the input of size S by H, and you need to transform it into the expert space, so multiply by the matrix N by H. After that goes the experts. In the experts, first part of the equation, we account for how much flops it takes to perform linear transformations. The second part accounts for this V-glue nonlinearity. Check out the block for why it is exactly 6 top K S F multiplier H flops. One thing to remind you guys is with MoEs, we don't activate all experts for a particular token. And thus, even though we accounted for n number of experts in the storage, when we calculate the flops, we only account for top K number of experts per token, which is much smaller. The last bit is our output embeddings or linear layer. We already know that it's 2 SVH flops, and we're done with our calculations. Similarly to model weights, we can now sum it all together, and for the parts that go into the decoder block, which are basically everything except for input and output embeddings, we multiply that by L, which is number of layers, add input and output embeddings, and we get the total number of flops we require for the prefill stage. So we were able to account for how much flops we need at the prefill stage. Decode stage will be very similar, but there we will focus on processing one token at a time instead of the full sequence. Well, this is true for all the layers except for one, which is called attention. In attention, we need to keep the context of all the previous tokens in our context window. So then we can perform attention compute itself. There we need to do a pairwise comparisons between tokens in the sequence. Notice in attention we have this S squared part. This is exactly where you need to have the full context and perform those comparisons. Well, if you process just one token at a time and have to go through all of the other tokens' pairwise comparisons, this becomes very costly. It grows as a S squared function, where S is number of tokens in a sequence. There is a solution to it. It's called Kiwi cache. There, we're simply going to pre-compute key and value vectors for all the tokens in the sequence, so then when the new token arrives, we only need to compare it to other tokens in the sequence and don't perform the other pairwise comparisons. Now, that saves us compute. So for number of flops, to account for number of flops in the attention with the Kiwi cache, we just remove this S part. It becomes cheaper. So it grows now not as a squared function, but linearly, which is much better. Now you need to account for additional storage because you need to store those key and value vectors somewhere. So here we have additional number of bytes that we need to account for when we run our model inference. Similarly to how we do it in prefill stage, for decode, sum up all of the operations you need to perform in a single decoder block, multiply that by number of layers, add your input and output projection computations, and you get total number of flops required for decode stage. Cool. So we were able to calculate how much storage we need and how many flops we will spend on running an MoE model inference. Now, our theory looks good, but unfortunately, it doesn't always match practice. So let's run an actual experiment and verify it. We will load Qwen3 3B active 30B total MoE model on H100 GPU and see how much time we spent generating one token. After you kick off this experiment, you can see the actual time spent. Now, after you break down where your time goes, you will see that 99.5% of your time goes for model weights movement. You need to move the weights from HBM memory to the SRAM. And only 0.5% of your time goes for compute. This is bad. What it means that right now you are in memory bound regime. In that regime, your model weights movement dominate overall time, and GPU stays idle, not doing useful computations. You are not efficiently utilizing your hardware and money. Now, the regime that we want to be is called compute bound. During compute bound regime, your GPUs runs at its maximum peak flops. So you are efficiently utilizing your hardware. So how do we switch from memory bound regime to compute bound regime? Let's introduce some metrics and find out. The first metric that we need is called throughput. Throughput measures how many tokens we generate per second. Now, throughput tells us how efficiently we are utilizing this GPU. Low throughput means GPU stays idle, and high throughput means GPUs are busy doing useful work. How do we calculate this throughput? Well, it depends on the regime. Remember, in the memory-bound regime, the one that we are in right now, the overall time is mostly spent on the weight movements. So the throughput is equal to bandwidth the speed with which you move those weights from HBM to SRAM for the GPU case. It's approximately 2.8 terabytes per second, divided by the model weights in bytes, how many model weights we need to move. In the compute bound regime, most of your time is spent on actual compute, and thus throughput can be estimated as the fraction of peak flops that your device has. So for example, for H100, we can say 800 teraflops divided by the algorithmic flops we spent to generate one token. Now, throughput alone isn't useful. We also need another metric. It's called latency. Latency measures how long your users wait between consecutive tokens. Users are happy if we generate tokens faster than the users can read, and they're not happy if we are slower. So this metric directly affects user experience. And basically what it means is if we optimize just throughput, and at a very high throughput, we have a very bad latency, that this is not a very useful inference server. So how do we define latency? Latency is equal to batch size divided by throughput. As we increase the batch size in the memory-bound regime, our throughput goes up. Well, this is because we are amortizing wait loads across more tokens. However, latency stays flat. This is because most of your time is still spent on wait movement. At the large batch size, you hit a transition point, after which your throughput stays flat. You've maxed out on compute. At the same time, latency starts climbing up. Well, that's because most of your time is now spent on the compute or not on the data movement. And adding more tokens to your batch increase compute. So here is our optimization strategy. Let's continue increasing our batch size until we hit the compute bound regime. Through the experimentation with the Qwen3 model, we found that it happens at approximately 256 batch size on a single GPU. Now, MoE models are tricky because not all the layers have the same batch size. Remember, MoE layers subdivide the batch size. Each expert receives only a portion of the overall batch. And thus, even though most of your layers can transition from memory-bound to compute-bound at a relatively small batch size, MoE layers will require a bigger batch size. And as you increase number of experts, that batch size go higher. To continue increasing throughput for MoE model, you might need to go to a larger batch size. But that will likely hit your H100 memory limit. So you would need more GPUs. When we split our model across multiple GPUs, let's use a version of model parallelism called expert parallelism. There, we shared Qwen3's 128 experts across multiple GPUs. Each MoE layer then performs an expensive all-to-all shuffle. It basically dispatches tokens to the relative experts on different GPUs. Then it gathers results back to perform expert mixing. Here is the problem. This all-to-all operation is very expensive, and communication becomes the new bottleneck for MoE models. Unlike a single GPU case where we could simply batch our way out of the memory-bound regime, here it won't help. Here, increasing the batch size scales both communication and computation. Go to the part 4 of MoE 101 series to get more details on this. So, to summarize, we've hit two walls. On a single GPU, we are memory-bound. On the multiple GPU case, we are communication-bound. Both come from the same architectural constraint when memory and compute are separate, connected by bandwidth-limited wires. But what if we had hardware that was compute-bound from the start? Let's take a look at Cerebras wafer-scale engine. To run inference on Cerebras WSE, we need to lay out our entire model on a chip. It happens in the pipeline mode. There, we need to map each layer of the MoE network to a physical region on Cerebras hardware. with its weights and key cache, but it all stores it locally. Now, regions are placed adjacently, so you won't notice any latency overhead when you move from one layer to the other. So remember, from our single GPU analysis, we spent about 25 milliseconds loading model weights from HBM memory into the SRAM. With Cerebras WSE, we don't have HBM memory, and we can load our model weights directly onto the SRAM. SRAM has 21 petabytes per second of memory bandwidth. Compare that to the H100 memory bandwidth. It's approximately 7,500 times faster. So with Cerebras WSE, our Qwen 3 model will roughly spend 1.4 microseconds to move weights to the compute units. You basically won't notice it. And because of that, you are compute bound from the start. And we can run inference with a batch size 1. And here is where we will pause. That's because we don't really need to run any experiments we did for the GPUs on Cerebras hardware. Let me summarize what we've learned so far. In the beginning, we defined our theory, how much storage we require, how much compute we require. Then we ran actual experiments and realized that GPUs can spend most of their time moving the weights and not doing useful computations. Then we introduced two regimes. One is called memory bound, when most of your time is spent on moving the weights. And the second regime is called compute bound, when most of your time is spent doing useful computations. We also introduced metrics such as throughput and latency. Those two can help us transition from memory bound into the compute bound. And through the experimentation and theoretical analysis, we found that by increasing the batch size to roughly 256 sequences, we can transition from the memory bound to compute bound regime. When we looked at the multiple GPU case, we realized that there is a new bottleneck. With expert parallelism, we are communication bottlenecked. This all-to-all shuffle operation is really expensive. There is no way to batch yourself out of it. Finally, we explored Cerebras WSE solution for inference. There, we are compute bound from the start, and thus no batching tricks required. You can simply run your inference with the batch size 1 and utilize your hardware efficiently. And that's the journey of running MoE model inference efficiently. So the key principles are understanding your bottlenecks, measuring the right things, and choosing the right hardware. Before we close, I want to say thank you. This MoE 101 series has been quite a journey, and I couldn't have done it alone. So thank you to all of my co-authors, reviewers, and our brilliant marketing team. Your contributions made this MoE guide what it is. I also want to say special thank you to my mentor, Landon, who encouraged me to do it in the first place. And all of you who have been following along, reading the blogs, watching the videos, and asking your questions. Your engagement made this journey so fun. We've covered the MoE 101 basics, the fundamentals you need to know about how to train and serve these models efficiently. But this is just the beginning. There is this whole world of advanced techniques, cutting-edge research, and real-world optimizations that we haven't touched yet. We are excited for what's coming next, so stay tuned.